in this video, we're finally ready to introduce the last axiom for the real numbers, which is called the Completeness Axiom. And you will soon see why it has that name. Okay, so we're going to start by comparing the rationals and the real numbers. And here I have a set of the rational numbers x such that x squared is less than 2. So okay, we know that square root of 2 squared is 2. So I'm going to draw it here. So any rational number less than square root of 2, indeed, when I square it, is going to be less than 2. And I want to find the supremum of that set. That is going to be my goal, really. So, but to do that, let's take a look first at upper bounds. Okay, so 1.5 is definitely an upper bound of the set. 1.45 is an upper bound of the set. 1.42 is another upper bound. And then I can find something in between square root of 2 and 142 that is rational. So that would also be an upper bound. And here you'll have to trust me for now, but I promise you I'm going to prove it later. I can always find in between square root of 2 and a rational number r bigger than square root of 2, I can always find another rational number. So as I said, if I pick a rational number r bigger than square root of 2, I can always find another rational number such that that number is between square root of 2 and r. Okay, believe me, please, for now, believe me. Then this means that for any upper bound x in Q, there is another upper bound such that y is less than x. That's what I was telling you, right? Between, if I pick an upper bound, a rational number x, I can find another rational number y in between square root of 2 and x. Okay, so that means that A cannot have a least upper bound, right? If I pick an upper bound, then I can always find another upper bound that is smaller than that one, but if I pick then the one that I got, then I will do that process forever, so I cannot find a least upper bound in Q. This is very important. We cannot find a least upper bound that lives in the set of the rational numbers. Okay. The least upper bound of this set A as a subset of the real numbers would be square root of 2. But square root of 2 doesn't exist in the rational numbers. Okay, so what happens here is that Q, the set of rational numbers, has a hole where the supremum of the set is supposed to be. That's why I say that this axiom, what is it, completes the real numbers. It is what encapsulates our idea of the real line has no holes in it. So that's what the completeness axiom is doing. It's just capturing that intuition that the real line has no holes in it. Okay, so, but how can we formalize it? Okay, let's see. The completeness axiom, or least upper bound principle, tells me that if I have a subset of real numbers, if S is not empty and S is bounded above, then S has a least upper bound or a supremum, however you want to call it. So you see, and that least upper bound is a real number. That didn't happen with the rationals, right? We had this set here that has infinitely many upper bounds, but it doesn't have a least upper bound in the rational numbers. It has a least upper bound, square root of 2, as, real number, but not a rational number. Okay, and we're going to show that. Perfect. So now that we have all our axioms, I just wanted to put it here. You have all the 16 axioms of the real numbers. We have them here all in a collection for you. So if you want, you can come back to this slide, take a quick look whenever you want to see all the axioms together.